So, welcome to my talk. First of all, thank you for inviting me to Devox in London. I love the city. I love being here. And most importantly, thank you very much for choosing to spend this last time slot, the last 45 minutes with me on the topic of resilience, robustness, and anti-fragility patterns in software development. I hope you will find these topics and patterns as enjoyable and insightful as I do. If you have any questions, please feel free to reach out during the presentation so we can maybe have a dynamic exchange on that. And let's start. So let me introduce myself. My name is Iryna Dohndorf. I'm an IT consultant at a Swiss consulting company named Karakun. We develop Java applications. We're crafting a lot. We also develop open source software, and it is in our heart to develop a sustainable Java community, and this is why me and my colleagues spending a lot of time giving talks or writing blog articles. You can find some of them, so some of my written blog articles on devkarakun.com. I invite you to read some of them and enjoy the talk. So this talk is actually inspired by a Norwegian professor of ICT called Kjell Jørgen Holle, and he wrote a book, Anti-fragile ICT systems. And of course, there are also a lot of literature, especially from socio-economic side. And yeah, I would like to start my talk with some video. Oh, of course, the sound is not working now. Well, but the video is just telling you, I've got a computer, and then error is coming up. And this is what we are dealing with as software engineers. We are dealing very often with situations where a computer says no, or our applications in production also says no.
Well, after reviewing your resume, I gotta say, I'm pretty...
Okay. For this we can spend time later. So, but the question remains how we actually can benefit from failures and errors arising in production systems or in ever-changing environments. So, of course, we can handle errors. But if we expect that system just handles known errors, it will become actually fragile with the time. Give me a sec. And especially, which means handling only known errors can have serious consequences. So here you can see some serious worst-case scenarios, but my message is just we cannot handle every uncertain situation, and environment is changing, software systems are changing. We have to build systems by design, be prepared for these changes. And so let's try again. Perfect. But actually, you already know we have tools, so we have formal methods and mathematical methods known to all of us how to deal with uncertainty. For example, fault tree analysis or Markov chains or fault tolerance methods. Here you can see, for example, a software failure rate, how it is changing for software systems and for hardware systems. The curve is different, it is a bath cube curve. But somehow these methods are not very popular in software development life cycle. And I think this will change because time and budget pressure is the only constant for software development practice, right? Also, communication is very important to deal with uncertain or maybe faulty situations. Well, but nevertheless, many of bugs are even not detected before the code is going to production, or even worse, we are fixing bugs and they go to production system even without testing. So I feel these situations are somehow known to us. But AI is changing software development fast and in scale. And what changes is actually that systems we are dealing with are non-deterministic anymore, and they require actually different testing approaches. So a binary green or red test is not enough anymore. And measurements of the systems become more critical. So observabilities or probabilities and performance metrics in that case are important to be able to evaluate stochastic behavior. Also, testing is thus more strategic for organizations and is not operational anymore. Well, this means that engineering practice will also change now, and it has to integrate correctness and probabilistic uncertain systems behavior, which is, of course, particularly important for some domains like safety critical systems or automotive or aerospace. Well, as next, I will give you some examples, and during my presentation, I will give you some patterns of anti-fragile system or maybe resilience patterns. So we will handle this topic through examples. And the first example I would like to present to you is a P-unit. It is an open source tool for Java, Rust, and R. And it is written for probabilistic testing of non-deterministic systems, for example, AI-enriched Java apps. So you can find the link in my slides, and I will show you why it is so interesting. All of you know the classic green-red testing in JUnit. So what traditional JUnit test does, here on the left, if you call a method LLM return sentiment, it will call the LLM and it will do some assertions. So assert equals, for example, if a sentiment is positive or negative. But the issue here is that LLM output can be very much different tomorrow or maybe in 1 week, and we do not have any guarantee for actual system behavior, which is highly non-deterministic in this case. So what P-unit does, it is an extension of JUnit framework. You can add a probabilistic test annotation, which in principle will run a test of very high sample size, for example, 100 times or 200 times, it is up to you. And it will treat each test run as a Bernoulli trial. And afterwards, it will construct a CI, so a confidence interval. So you have some kind of solution. You can ask the question, does my test pass with a probability higher as an upper bound of your confidence interval value? And here you can see this through pass rate meeting, where you can specify actually your success probability, and you can specify your service level agreement contract in that case. Well, for the use case, it is a central approach in P-unit. you do have an outcome and the so-called postconditions, which are called after some positive outcome of your call, but you also can specify a pass rate meeting and some value. Well, this outcome is very interesting, and this leads us actually to the other possibility to treat uncertainty. So here we have an example of LLM, right? But actually it is a great way to treat a call to any external or third-party system, which can also be successful, but it can also fail, right? So, and the advantage of an outcome is that you just can save the outcome of your call. Well, in the happy path, if invoke method is called and outcome saves an OK method, otherwise for the error path, you will just count the probability and the failing test in that case. Well, with p-unit you can explore, which means you can turn your parameters, maybe for your LLMs as a temperature. If you have some kind of continuous parameter, it is possible to experiment. You can also optimize your parameterization and measure, which means you will determine a baseline. And when actually testing your framework, you will just see how it is behaving in comparison to a baseline. Great. So this brings us to the actual definition. So let's take a closer look what it means anti-fragile. Well, anti-fragile systems, they need errors and failures, uncertainties and disorder to learn from them and become stronger with the time. So here you can see an example of a tree which has to be exposed to wind to build a stronger roots, for example, or a human immune system is the same. And the idea of anti-fragility is that with you need actually failures and errors because you can learn from them, maybe also in the online mode, and such you can optimize your system configuration or implementation. Well, as robust system, for example, they're just unaffected by a malfunction, so they are able to handle somehow to handle errors. But if you have built your robust system, which is of course a first step to anti-fragility, with the time it will become fragile because the uncertainty of your environment just increases. So APIs are changing, disorder is increasing, maybe formats are also changing. And this is the idea. Yes, you can also say that if you have an anti-fragile system, it learns to perform under pressure. So
Impressed. Tell me a little bit more about your skill set. Well, I'm a critical thinker, I'm hardworking, and I can perform under pressure. Well, that all sounds pretty excellent to me. You're hired. Listen, sir, I gotta let you go. You haven't done a single ounce of the work at all. Sir, you're not even using a base.
Yeah, so this is, of course, not what I mean when I say how to perform under pressure, but now you have an idea, and I will give you some more examples. Well, the first one is the so-called LLM prompt injection tool. And I'm sure you have been in some presentation at Devox where LLM prompt injection attacks were covered. And I would like to present to you a one tool called Augustus, and Julius, a friend of mine, recommended to me this tool, and it saved really my day, and it saved my chat bot implementation. So what it is a vulnerability scanner developed by Praetorian, and it is a single Go library which has a lot of probes which are hard-coded, and it can serve a quite number of LLM providers. And how is it working? I show you in the code. So Augustus is a command line tool, so which means you can make a simple call where you can specify a provider, you can put your key, you can specify also a model and a temperature, and the most interesting thing, you can specify some probes on that. So I can really recommend to you to use this tool if you have any LLM in your application, because you can test the safety of the model. But why it is so important for resilience? Because you can analyze failed probes on that. It's for example in form of curl, so you can really see and analyze which calls do not pass the LLM safety test. And writing a Java wrapper for this tool, which is not a very complex task then anymore, what you can do, you can integrate actually with a test annotation, you can integrate this test into your CI. So you can identify already safety issues during your CI, and you can actually feedback them into your system prompt. So this could be very helpful if you especially work with AI in Java applications, but you can also do it in Rust or Go. Great. The next example I would like to show you is about how Netflix actually building its robust and resilient systems. So you know that each time we are watching a movie, or maybe getting some recommendation, or somehow searching for results, Netflix is processing really big amounts of data every second. But the accidents they are dealing with can be really severe. So, for example, downstream service outages, network errors, or maybe data update issues or fail data applications. So what Netflix did, they actually built the so-called write-ahead log architecture, which can be plugged into different services. And of course, they do automatic learning for that. And of course, they perform a lot of chaos engineering. But I find this architecture particularly important in an era of AI agentic development. So please consider to integrate WAL write-ahead log in your agentic AI workflows. It helps a lot to build resilient and robust systems, and I explain you why. Because it uses separation of concerns in terms of message producer and message consumer are completely different components in the architecture, and each of them maintains a queue for messages which are coming from client applications and a dead letter queue to treat somehow replies for messages which somehow failed. It also has a durable store and a very flexible target services as caches, databases, queues, or further upstream services. So this flexibility is quite important if you want to build resilient systems. And in the control plane, it is a Netflix architecture. They just use it to automatically configure queue number or maybe client application or downstream applications, which enables, for example, to scale fast and to adding different message consumers, or for bottlenecks, if they appear, you can add queues. And what is interesting is the so-called config store, where you can just change namespace configuration at runtime and, for example, duplicate a queue required in Surface. Yeah, how it works. If a request is failed, for example, a request to a Kafka stream, then the client application will send a request to a write-ahead log. Write-ahead log is the so-called wrapper class, so it will take retries or big-offs or health checks on its own. And I think this is a very interesting idea. Yeah, and of course, if the request fail after specified retries, it can save them or save failed messages in a predefined queue for that. Yes, for example, here you can see that Kafka dead letter queue will be filled in if all attempts failed, all attempts to process a failed message. And afterwards, it can be saved to further data storage to handle the messages afterwards. So consider this wall architecture maybe for your agentic AI implementations. If you have agents and they're dealing with data or processing data, writing data from A to B, this can be really helpful because normally you don't know what they are doing. It is like a black box. So the wall write-ahead log gives you some kind of control what agent is actually doing. And of course, you know they're trying on their own if some task couldn't be finished. But I think this concept can be really helpful. Great. Let's take a look into some technical principles and aspects. I'm sure you know some of them, so we can only go through. Modularity is, of course, great. So monolith is not always a bad thingy. This is true. There may be a lot of good reasons for monoliths, but modularity makes systems, so it prevents failure from spreading into subroutines or components in your system. So consider this as a very practical example, could be microservices. Yeah, and of course you have advantages like fast development cycles or increased fault tolerance, and of course complexity of management can arise. In terms of modularity, message producer and message consumer, so the separation of concerns, or maybe also queues like dead letter queue, are very good examples how to introduce modularity into your system. Weak links, so isolation. Maybe one of prominent examples of modularity and combined weak links. Maybe if you are using Docker, you already know that Docker released as sandboxes for agentic AI environments, which I think I do not have a dedicated slide for that, but I think this is a great example for current software development issues. So weak links are great because you can identify your problematic connections, or connection which can fail, and you can reduce the negative effects. So you can convert actually strong links into weak links, and there are some patterns as retry pattern, for example, or health check or fallback. So we can take a look. Timeout pattern. I think this is a very simple one. So goal here is to prevent a call from being blocked. If you expect a call and a response to happen in some predefined time, you can define a timeout and handle your failure then. A retry pattern is also very interesting because here you also gain a possibility not only to retry and possibly, you know, exponential backoff algorithm, but here you can also apply some data science methods. So if you have sophisticated application with a lot of calls, maybe up to hundreds, and you have a really high reliability requirements in your system, it could make sense maybe also to estimate the time required for the next retry. And here I just wanted to show you how to do this. So you can estimate the time. You can see in time the time as a network time, for example, or required for your calls, which can be collected into time intervals and then be used to determine some probability distribution for the time between calls for your happy path, for example. And this gives you an additional tool, maybe some it is stochastic in some kind, but it gives you a possibility to drop from the feature distribution and to determine the time for the next call. So this would be an example of a learning and a feedback loop directly to your system. Circuit breaker is, of course, still important. Why? Because circuit breaker gives you an opportunity for an external system, for example, to heal. It has 3 states: open state, half open state, and closed state. And the goal is actually fast detection of errors and then to prevent some system overload. You can just wait a predefined time until next call to the attached service can be executed. Well, the next one is a fallback pattern. It is a simple workaround the error. And here I would like to show you a use case when you're working with AI-enriched applications. For example, let us take a chatbot service, a Java application for a chatbot. So you will have some LLM provider in your model. And your Java Spring Boot application, for example, is reliably very strong on your LLM provider. So in principle, when it is not working, your application, if you do not have any appropriate failure handling methods, it will also fail. So you will need some kind of retry logic, for example, to retry after a delay. This could be a back-off mechanism or a circuit breaker. And of course, if your retry is not successful, your LLM request fails. So in that case, you can just print out a default response. But most interesting could be the scenario where you have more than one LLM provider. And if one fails, you can still use the second LLM provider or the third LLM provider. And you can put them into priority queues, and then it is up to you how to define maybe a priority based on the health of your LLM provider, or possibly on the cost, or on a token usage, or maybe on a probability of failure. Maybe it returns some unexpected response or unsafe response. So it is up to you which parameter to observe and how to define the priority of LLM provider to use. How it can look like. So in your application properties file, you could then, for example, specify the type, the key, so the parameters of your LLM component, and you can also specify a priority which can be fixed or which can be computed by an algorithm you specify. Here's an example. I would like to show you a so-called LLM provider cooldown. So the idea here is, so suppose you have 3 providers, OpenAI, Google Gemini, and local Ollama model. If one of them fails, you can still determine the second one provider to choose, and you can put the failed provider into your config store, for example. You can also define a temperature for a cooldown time, and you can adjust the configuration in the config store in that case. And as cooldown time expires, for example, the Google Gemini here will be put into the queue with initial priority, so your application can still rely on that and it can be used. So you can use this example for the self-healing mechanism. Another example I would like to show you is how to use resilience for J library. It gives you a circuit breaker and retries in your application. You can then use these annotations, for example, as a fallback method. You can specify which method could be used in case of fallback, and it is then just called in case of failure or when your API is not available anymore. Yep, but this was just a small selection of methods. You can see that the landscape is huge. And of course, I could spend hours to talk about them all. So please take a look into the source on Git. Redundancy is, of course, very important, but also diversity. I think this is also particularly funny because it is not very common in practice. What does it mean, redundancy? That, for example, a component or a module can be written in maybe in another language, like in Go or Rust, or maybe a compiler introduces some variants into your code. So you can just add some diversity patterns and thus also decrease the probability of having vulnerabilities which may be present in some language or components. Well, operating principles, it is also a very huge topic, but I think the most important of operating principles is fail fast, so you're able to handle the error very fast and to learn from that, but also to have a skin in a game. So as a software developer, this is also a very important skill in the game, means we, as a software developers, be really responsible for projects we are building and for the code we are delivering to our customers, and for functions and also for dysfunctions, which does not mean to be blamed for something goes wrong. No, it just means to learn when failure occur and to be responsible for that. So consider please. And fault injections would be the next topic I would like to present to you. Fault injections are some kind of testing disciplines, and it is actually the resilience testing. So all of you know the unit tests, integration tests, but resilience testing is underestimated. Please consider to introduce these test types in your practice. So this is actually controlled failure situations. Or stress testing systems by introducing faults, for example, like we saw using Augustus or Julius, penetration testing tools for large language models. It is also possible to do a compile time injection or runtime injection. And what could be interesting to test, for example, database disconnections or memory excursions. What is validated then? Your failure modes, your error handling strategies, if they are working or not, your redundancy, and your failover mechanisms. So, and there are a lot of tools, especially from the chaos engineering, like ToxiProxy, Feed, Netflix, Chaos Monkey, and I think most of these principles are now slowly diffusing to the Java ecosystems. But they are particularly interesting. But how fault injection actually works? First of all, you have to identify a target. What is your critical component to be tested, like API, database, third-party system. Specify your fault, so define a scenario, for example, API timeout, or missing response, or process is killed. Thirdly, the fault application, so you really need to inject a fault, either in a manual test or using tools. Of course, observation and improvement are the most important steps here. So you need to monitor system responses, recovery times, error times, maybe to not only observe and measure, but also trying to use data science tools to obtain some performance criteria. And improvement, so you have to optimize your implementation, your configs and architectures. I would like to show you a sketch of a tool for resilience testing of Spring applications via fault injections. So you will find a paper under the source defined here. So what it does, it identifies automatically tests in your applications via which are annotated through Spring Boot test annotation. And it uses manually written recipes. So here, for example, recipe for abort a message. You will, for example, identify destination. It would be an endpoint ping, and the method would be a post. Or a delay recipe. Destination method would be a post, pong endpoint, the method would be get, and the delay time will be 500 microseconds. So, and using such recipes, the system generates firstly Maven testing commands, and then it injects faults into modules holding the implementation for these endpoints. Afterward, you can collect results and use report for improvement. So it actually simulates failure when matched services are called in tests. Here you can also see an example for get and category. So the faults will be in the category rest.java. This is a line number. And you can also specify further parameters. For example, if it is a post, you can specify a payload, maybe some malicious data to use. And of course, you would expect 500 internal server error in that case. This would be a recipe instruction. And when you have a match against discovered services, so it actually uses aspect J technology to identify methods in communication channels of security of Java Spring applications, and using this method extraction at runtime, so at your test runtime, the services are matched and the failure is injected. So when service has been matched, then the tool will actually call, it will throw an error, for example here, an internal server error, or in case of delay, it will call thread sleep. So you can actually inject faults and you can test your retry strategy, right? So in recipe, it would be possible to define injected once, once, 2 times, or 3 times. So you could test actually your retry or your health check component. Well, in case of large language models, the landscape is growing rapidly. What you have now are, of course, these are also LLM API faults if you are using external provider as timeouts or token limits or malformed responses. But you will also face tool execution faults or memory faults and also content faults, like example hallucination injections or safety triggers or format errors. So the landscape is growing, and actually for all of kind of these errors, you would need a mechanism to test, to inject the failure and to test your strategies. Well, and the last topic we will cover today is at automatic bug repairs. And it is a fascinating topic because imagine already in 2025, Google and Amazon are using LLMs for bug fixes in their production systems. So they really do automatic bug repairs in their pipelines, and they fix already 15% of the so-called sanitizer errors in their pipelines automatically using Gemini Pro. So it is you know Gemini Pro is actually a very common model. So I know 15% doesn't sound very good, but it is up to maybe hundreds or thousands of bugs which can then be repaired automatically and fast, which means that vulnerabilities are now spreading very fast in production systems. And so what they do, first of all, they find bugs through sanitizer tools, which are running on test instances. It is done, for example, overnight or when services are not overloaded, first of all. And imagine these are really small, are really very common bugs, like, for example, uninitialized values or race conditions, or maybe API errors. So very common things which are present in legacy systems, still present there. Then they reproduce and isolate the bugs, and then they generate fixes with LLMs. So the main idea here is that for different types of bugs, different models perform in better or worse ways. So they're using T5X or Gemini Pro or Cloud Vertex UI, and the prompt is very simple, so they do not waste time on very sophisticated prompt generation. So they just put an error detected by a sanitizer and a stack trace, and then they give some tries to LLM to fix them. The fixed code then goes again to a testing pipeline, and yes, and that's all actually. Of course, in very sophisticated cases, they need a human in the loop, but still 15% of these bugs can be fixed manually. And I think this is very fascinating stuff, because the methods are already available to us. These are, of course, machine learning methods, observing of errors, and using your testing pipelines. It is possible really to advance your testing strategies using automatic software repair. I think the predefined templates or example-based templates can work very well for simple error cases like uninitialized values or maybe common bugs. So please consider that. Yep, and doing so, you can use the so-called fix recommenders, which just generate code or use some template methods to generate and to validate actually the output. What is interesting here that you can change operators, maybe in some simple cases, so it is really a combinatoric task in that case. You can change operators or maybe API methods, which can be called. So these atomic changes and predefined templates, as well as example-based templates, allow you relatively good fix rate for automatic bugs in your testing pipeline. Yep, and as such, this brings me to the end of my presentation. Thank you very much for spending time with me on the topic. I hope you find it as enjoyable and insightful as I do, and please use resilience and robustness patterns in your applications. You can never do enough. And please do such when your system is already in production, but also when you are starting your implementation. Thank you.